Right, so back to a little bit of organic chemistry, right? So I've got an oxide, well not this bit, but that bit. This oxide contains 63.64% nitrogen by mass and has that density. I need to determine the molecular formula. So it's an oxide, so it only contains nitrogen and oxygen. It contains 63.64% nitrogen, which means it's the rest of it, which is 100 minus 63.4, which is 36.36, must be oxygen. So that's my percentage. I then divide each of those by the relative atomic mass, which is 14 for nitrogen, 16 for oxygen. So I will do that. That comes to become 2.27. 63.64 divided by 14 gives me 4.55. That's the smallest one. So you divide by the smallest one, that becomes 1, that becomes 2. So it is N2O, and that's my empirical formula. I've got to use this. It tells me it has a density of 1.833 grams in 1 decimeter cubed. It's a gas. The key thing at room temperature and pressure. So we know that 1 mole of any gas has a volume of 24 decimeters cubed. So if I times both of those by 24, so I would do 1.833 times 24, that gives me 43.99 grams in 24 decimeters cubed. That is its molar mass. Okay. If I do 2 times 14 plus 16, which is what I've got there, 2 times 14 plus 16, that comes to 44, and therefore that is also its molecular formula as well. Right, so we now shimmy on to some organic chemistry. I've got, you may sort of like go, it's a crazily complicated molecule, but what is it? Well, I've got a benzene ring here, and I've got a carboxylic acid group there. So those are the two groups you should be considering. I've got to suggest a chemical that reacts with ibuprofen to produce a gas. What could it be? Can you think of something that reacts with benzene to produce a gas? Well, not really. You know, although if you do, if you add bromine with a halogen carrier, you would produce HBr, I suppose, but generally that's not going to be. So the obvious one is it's going to react with the carboxylic acid. So if you added sodium, for example, you would produce H2 gas, and the equation would be, if I draw this out like so, plus Na would go to give me that's going to become the sodium salt, and then I also make plus a half H2 gas, like so. Okie dokie, on to part C. I've got local anesthetic here, being injected, contains that. This is one of the medics. What's its concentration? Okay, so I've got 100 milligrams in 5 centimeters cubed, and I need its concentration in moles per cube. First thing I would do is convert this into grams. Milligrams into grams, you divide by 1,000 to give you 0.100 grams in 5 centimeters cubed. Then I convert that into moles. So I've got a mass, I need moles, I divide by the molar mass. So it's going to be 0.1 divided by that molar mass. If you calculate it, it comes to 236. That equals 0.1 divided by 236 is 0.0000424 moles, but that is still in 5 centimeters cubed. So So its concentration in moles per decimeter cube is 0.0000424 divided by 5 times by 1,000 to scale it up to 1 decimeter cubed. So divide by 5 times by 1,000, and that gives you as being 0.0847 moles per decimeter cubed. Okay, so this is quite an interesting one. I've taken this, it's an organic compound containing carbon, hydrogen, oxygen. I've taken 1.394 grams of it, burnt it in oxygen to produce 3.74 grams of carbon dioxide and 0.18 grams of water, and I need to work out its molecular formula. So, I'm going to work out my moles of CO2. That is going to be 3.74 divided by the molar mass of carbon dioxide, which is 44, and that gives me 0.085. Now, that has got to be the same as the moles of carbon, because in every one carbon dioxide molecule I've got one carbon atom. So that has got to be the same. Moles of H2O is going to equal 0.918 divided by 18. That gives me 0.051. But every one water contains 2 hydrogens. So moles of H is actually 2 times 0.051, which gives me 0.102 moles. Okay. Right, I've done that, so that's okay. I now need to work out how many grams. So if I do that, I can now work out mass of carbon I must have had is going to be 0.085 times the molar mass of carbon, which is 12. So 0.085 times by 12, that gives me 1.02 grams. The mass of hydrogen I must have had is going to be 0.102 times by the molar mass of hydrogen, which is 1, which gives me 0.102. So the mass of oxygen I must have had is going to be 1.394, which is what I started with, minus my carbon, minus my hydrogen. So that's 1.394 minus 1.02 minus 0.102. That gives me 0.272 grams. Right. Now to work out a formula, I need moles of everything. I've got moles of carbon, moles of hydrogen, so I'm going to convert that into moles of oxygen, which is 0.7272 divided by 16, which gives me 0.017. Okay, so I've done that. I now need to work out my empirical formula. So I know it contains carbon, hydrogen and oxygen. It's got 0.085 moles of carbon, 0.102 moles of oxygen and 0.017 moles of oxygen. What's the smallest one? The smallest one is oxygen. So I divide each of these by 0.017. That will become 1. That becomes 6. And that becomes 5. So my empirical formula is C5H6O. If I add that up, I find the molar mass of that, 5 times 12 plus 6 plus 16, that comes to 82. They've told me the molar mass is 164, which is half, 82 is half 164. So the molecular formula, running out of space here, is C10 H12 12O2. Okay, so this is a bit of a mega question, but rather nice. Unlikely you're going to get this kind of question now for 20 marks, but you never know. So first of all, we've got to do some definitions. So I pop these up for you. You've got transition element, D block element that forms one or more ions with an incompletely filled D orbitals. Complex ion, transition metal ion surrounded by ligands, and a ligand is an electron pair donor that forms a dative covalent bond with transition metal ion. Well worth learning those, because you know it could be one or two relatively easy marks. You've then got the equations that you need to know for transition elements. First one, ligand substitution, copper 2+ plus chloride ions, giving you the chloro complex. So I'm substituting the water ligands for chloride ions, and that goes blue to yellow. Precipitation reaction, copper plus hydroxide ions give me copper 2 hydroxide, which is a pale blue precipitate. And a redox reaction, zinc reacting with iron 3+, give me iron 2+ and zinc 2+. That it goes from yellow to green. You know that because Fe3+, you know, is like a yellowy colour. Fe2+ is a greeny colour. Those are the two of the ions that you do need to know their colours for. Okay, we now need to draw some complex ions for part B. So let's do an octahedral example. Remembering if I do copper with water, to just make sure that your dative covalent bond always ends up at the oxygen, and that is 2+, of course, so that's octahedral example. Square planar, you may want to do cisplatin for that one, because that is one you need to know. So you've got Cl, Cl, NH3, NH3. That would be the cis, but you've also got trans, so you can use this example to demonstrate cis-trans isomerism as well in a square planar complex. You've also got optical isomerism as well if you have 3 bidentate ligands. So let's do an example of that. So it's going to be nickel, just draw them out. Probably easier to simplify. Well, I'll tell you what, I won't simplify, just to try and do it properly for you. So you just connect your nitrogens up like so, and then so that's one. That's actually a nickel 2+. So I'll pop him in square brackets 2+, and then you want to do your other optical isomer as well. So do your bonds around nickel. Like so, put your nitrogens on, it makes your life a little bit easier. Then just connect up the mirror image of those, like so. And of course, these are your 2 optical isomers, as so. Clearly, you can give other examples, so you could also give examples of cis-trans isomerism for monodentate ligands in octahedral systems as well. So if you change perhaps 2 of these for nitrogen, you know, sorry, whoops, that should be an H2O there. Whoops. Let's just do that. That would be the trans. If I put that back as being water and change that to nitrogen, that would have been the cis isomer as well. So it's well worth learning your complexes. Try not to make ones up, so that if a question does come up like this, you can actually state, recall all the different complexes you